I think most of the audience will be very interested because today our session is about data-driven methods, machine learning, and how we can use this kind of new tools in our engineering work. And I'm really happy that today I think we three speakers covers exactly the three important topics about a potential application of machine learning. We develops solver, and Hongbo learns physics, and Steve, you are mostly working on the data mining. So data, physics, and solver, I think is a fantastic combination. And so actually, I think the first question I think we can probably discuss is, what do you think is the most important thing to combine physics and data and solver? Probably these three things together. Is there any opportunities that you can see?
I don't mind going first.
Yeah. Feel free.
So I think definitely from my perspective, I'm not an electrochemistry expert by any means. I love my image processing, but I don't know like the electrochemistry that deeply. But from my perspective, for me, the next stage of my work is like looking at optimization, and that obviously like is very linked to being able to extract all of those metrics that the other two speakers were talking about. Are very interesting. Being able to extract those metrics very fast and do that and like try and get analysis of behavior very quickly. So I definitely see a space for like Bayesian optimization loops where we're generating microstructure, extracting performance, and then looking for the best possible like link between manufacturing parameters and performance. Yeah.
Great. Yeah.
I think the things that Stephen Wei do, I think it's quite connected to what we're also interested in, right? Because we really need the input, like for example, like microstructure and also mechanics to really need those like things we learn from there to incorporate that into the physical models for simulating realistic batteries, right? So I think especially yeah, we also have this paper recently, right, on reviewing this kind of effective microstructure, and I think there's really a lot of opportunity to incorporate that realistic microstructure with the physical models, and I think there's very little work actually done in this area. Yeah, so a lot of physics simulations we do is like not really concerned with the realistic structure.
Yeah, but by the way, Hongbo, we just finished a review paper. I think it will online soon, probably this week, on advanced energy materials. So everyone, if you're really interested in microstructure plus physics learning, I think that will be a very good review paper for you to look at. Yeah. Oh, Tengo, I see you turn on the camera. Did you have any comments?
No, I don't have any comments. I think it's very interesting, and thanks for inviting the three speakers. I'm just want to learn this. Yeah, I think you mentioned this like a solver and physics and data, like driven data analysis. For the first talk, I'm a little bit not clear to me about the solver. Like for the training, like in the numerical simulation, we need to discretize them into like nodes. We can use a finite element or finite difference for different methods. Then like what's the connection between the machine learning and the numerical calculation? Do you still need to use this discretization like a numerical calculation, or everything you only need the position and everything you can do in the machine learning?
I guess I can answer the question.
Yeah.
Like, yeah, in finite elements, we need some nodes and mesh. But in machine learning algorithm, you can randomly sample this kind of nodes, but we don't have like special requirements on the like for example, in finite elements, we need a mesh to be very like regular. It cannot be distorted. But I guess in machine learning algorithm, you can just randomly sample those nodes. So you don't need to consider the quality of the mesh. I guess that's the difference.
For the geometry with the hole, then like how to describe? You have very complicated geometry interface?
Yeah, so you can sample those laws within the domain. So yeah, that's one problem. Like you have to sample enough data points to make sure you can represent the like a shape with a hole or some complex shape. So for those kind of shape, we need more loads.
Yeah, I noticed there's some like a neural network method that people call the graphic neural network that they can embed it, embed this connection geometry information in your neural network. So are you familiar with that kind of design of a neural network?
Yeah, I heard of that, but I didn't personally try that. Yeah, maybe I can have a look at that to see if we can like, incorporate those like some different neural networks to this physics-based learning like, framework. I guess that's also possible. There is no like requirements from like you must use some kind of neural network. You can choose any kind of network. I guess we can come up with many ideas to implement those physics. So my example is really very simple.
Okay. Yeah, maybe also related for the last talk for the image. I think people also use some like adaptive, like messing, like for the interface, you may have higher resolution. For the uniform, you have this coarser like points. I'm not sure whether like ways like this method you can say for some regime you can sample like less, some regime you sample more. Maybe I think there's some connection between the imaging analysis and the solver and the like a solution. Yeah.
Yeah, I think unfortunately one of the problems with convolutions is that you need a uniform sampling of pixels, right? Your convolution is like a kernel that runs over your image. So if you have a high resolution in some areas, certainly you would have to change the architecture quite significantly. There would be ways around that, but there would probably be quite complicated architectures of neural network. But it is a really interesting idea because you could save a lot of the memory costs that I was talking about earlier. If you manage to do that, you could save a lot of memory. Yeah.
Okay. Yeah.
Yeah, I think Tan just mentioned a very fundamental question. And actually, in my opinion, in Waze solver, there is no data at all. It's just coordinates. So how to combine real data with some physics is really a challenging part for us. And Steve's work, I think, is touching the fundamental base of that question. Yeah. Okay. Yeah.
Okay. So, yeah, I think yeah, others can discuss. We can discuss more.
Yeah. Okay, that's great. And I think probably there will be more applications. So I think probably time is limited. Probably we can just discuss one more question. For example, what is in my mind is, so what do you think, because batteries is such a complex system, and what kind of other applications that three of you and all of us can think about? Do you think machine learning can do more for us, or is that any concern from you for more battery applications? I mean, all kinds of data-driven methods, not only machine learning. Maybe Hombo, you can start first.
Yes. So, well, I think that's a really broad question. From my perspective, I think that I'm personally very interested in knowing the fundamentals of the batteries. So I like, for example, I would like a data-driven method to be able to tell me, like, what are the physical properties, right? A lot of things that my concern is that the machine learning is that it's a black box. So that's why sort of I'm more starting from the PD constraint optimization perspective, where and also Wei's perspective, right, including the physical constraint. I think that's I think that's very important in terms of interpreting what we get from machine learning.
Yeah, very good point, I think. So Steve?
Yeah, I think the black box point is really interesting. I definitely, it is more and less important in different areas, I guess. For me, there's a sense in which it's a black box, but I don't really mind, because as long as the images that come out the other end fit the like statistical distributions that I expect them to, I don't really mind. I don't need to understand it. But obviously, when you're trying to extrapolate on information, or even interpolate between different types of microstructure, suddenly being able to understand what my black box is doing becomes really important. So it really depends on the applications there. I think also it's really, so like I came from a material science background, hadn't done any machine learning. It's just very fun seeing like all of these like really cool techniques being applied in areas that we didn't know they would be useful. We developed these complicated neural nets to recognize features in people's faces, and now like we're just applying it in material science. It's cool.
Yes, it is. Yeah. So Wei, do you have any comments?
I guess I basically agree with Hongbo. Like we need to include the physics, but I guess in my examples, it's all about physics. There's no data. I guess
Yeah.
more promising ways to combine the data and solve and the physics, not solve.
Yeah, and I can see that actually really how to combine these two, because in real world, I think most cases we have some data and some physics. Physics is not clear and data is not sufficient, and probably these two, how to put them together to train our algorithm, that's a very big challenge in my opinion. Yeah. Yeah. Is there any questions and other comments from the audience? Oh,
I have a general question. Yeah. And still, like we are familiar with like the numerical method, we know that like if we have this method algorithm, if you change the problem, you can get still use the method to solve the problem. Like for the machine learning, if you get some training, can you know what kind of problem you can still use the same trained network to predict? Or like is there a way you can say you can continuously keep increasing your scope you can predict?
I guess if we use the machine learning as a solver, it will be like fundamentally the same as the other solvers like FEM. So when you have a different problem, you can also use the same framework, but you need to train the neural network again. Like you are using finite element methods. If you have a different problem, you also need to solve the problem again, right? I guess in this way they are similar.
Yeah, my so my feeling is like for the machine learning training, you not only train the PDE, you also include the boundary condition and but if you train problems with certain constraints, certain boundary conditions, then if you have some new problem, your boundary condition is different. So will that be a problem?
Yes, you can always like include those like changed condition into your framework, as I guess essentially they are similar. As you said, if the boundary conditions are too complicated, it may the solver based on neural network may be not so efficient as compared to the FEM, maybe.
Yeah, I can actually partially also comment on this. I think it's Teng's question is mostly about the is machine learning algorithms or method, transferable. The knowledge is transferable or not. If you change some boundary condition, can you still use this? And I think this exactly, I think, can be covered partially by Hongbo's talk. if we can use this kind of tool to learn physics, then probably the problem will be universal, and what you learn is universal. But to waste PD solver, I think it still depends on, you cannot transfer the knowledge to another question easily. And you have to, for another boundary condition, you have to retrain your model, right? So that's the problem, I think, more or less. But it's kind of just a finite element code, but probably have some potential applications. Yeah. So, and Steve, there is one more question for you, I think, from the audience. From
yeah, I thought I'd just share my screen quickly to answer this. Can you see that?
Yeah.
So we can, the question was about whether we can do continuous materials as well as end phase, as well as like end phase materials. So you can see here, we've done the reconstruction with like a grain material. One of the problems is, again, like I've just started out on this, so my GPU is not particularly large, and 3D convolutions are very computationally expensive. So this would probably be significantly better if I essentially had just like deeper networks and more filters, but it is possible, is essentially the fast answer.
Great to know. Yeah. Looks very fancy. Okay. Yeah. So I didn't see your the paper in Nature Machine Intelligence. Is that online?
It's being published tomorrow.
Tomorrow. Great. Great.
It's available on archive. Yeah.
Okay. That's great. Okay.
Yeah.
Okay. Do you have any more general comments or questions?
Thank you very much for hosting. It was
Okay,
really
thank you.
to tell the talks.
So I would like to thank all the speakers and all the panelists and all the audience. So it's really a very nice discussion for me as well. And I learned a lot from the 3 speakers, although I actually is a collaborator between 3 of you. Actually, I'm working, Steve, I'm working with Sam as well. so actually I learned I know part of your work, but today is so informative to me. Okay. And I also would like to thank Bahong and Xiaoting for organizing. Okay. Thank you, Bahong.
Okay, thank you, John. Thank you all speakers and the audience come to the webinar today. So see you next week.
Okay. Bye.
Bye.
Bye-bye.